Hello once again, AP Calculus, AB students. Mr. Record here from Avon High School, and you are taking a look at the first video in our section 2.5 from Larson's 9th edition textbook over the topic of implicit differentiation. And I think the best way to sort of introduce the idea of implicit differentiation is to show you the difference between a function or equation that you could have easily taken a derivative prior to this section versus the new look of these equations that require the use of implicit differentiation. So I'm going to read this along with you. It says, up to this point, you have learned how to differentiate functions that are expressed in an explicit form. We're now going to take a look at relations written in an implicit form. Note the differences in the two types of functions from the table below. So as you can see in the first column, we have our explicitly written functions. And you all, at this point, should be able to take the derivative of either of those two successfully. The first one is just a very simple application of the power rule. And the second one would be a little bit of a chain rule, but nonetheless would be a pretty easy derivative to take. Now, compare those two equations with these two equations. And I'd like to ask you, what is it that you know that's different about the two? And if you're thinking, on the left side, y, or f of x, is by itself, you are absolutely correct. That's how you define an explicitly written function in this case, or an explicitly written equation. Over here, we've got x's and y's just all sort of mixed up, and I've actually given two pretty complex implicit equations here where it's not so easy to solve for y, at least with the mathematics that we know up to this point. So whenever you see equations written as such, you have a slightly different approach with your derivative. Now, I want to make sure you all know they do have derivatives. In fact, these kinds of equations will graph some of the craziest looking graphs that you would ever see. And in some of my later videos, we'll take a look at that by using the TI Inspire graphing calculator. But for right now, I just want us to be able to find a procedure that would allow us to take the derivative of equations written as such. So on the next slide here, my first example, we're going to take 4 very quick practice problems, and we're going to differentiate with respect to x. Now, it starts to become very important in calculus that we understand the meaning of that phrase, with respect to x. That is saying that you would take the derivative where x is acting as your independent variable. Any other variable that is not an x has to be treated a little differently. It has to be thought of as some foreign variable. Perhaps we could even think of it as a U substitution type of variable. And you're going to see that the door is going to open up once again to be using a chain rule approach with these problems. Well, for part A, we don't have really much to worry about because the derivative of x cubed with respect to x follows the very simple power rule that we learned a chapter ago or a unit ago. And in this case, we would get 3x squared, and that is it. That's all we do. Very simple. So you might think, well, what's different about implicit differentiation? Well, we go to part B in example 1, and we find that we are now differentiating y cubed with respect to x. Well, as I said before, you want to think of this as sort of some value u to the third power. Or sometimes in class, we get away from using the letter u, and I'll just use the word something. We're taking the derivative of something to the third power. And if I ask you all, what is the derivative of something to the third power, you would say, well, that's equal to 3 times that something. Now, I don't want to write the word something here, nor do I want to write the letter u here. I want to identify exactly what the u is, and that would be the y all along. U is equal to y. The something was the y. And of course, that power of that something is going to diminish by 1 to 2. But wait a minute, we're not quite done. Because if we were done, there would really be no difference between handling a problem like Part B versus Part A. But there is a very big fundamental difference. We have to complete the chain rule in this problem and actually multiply by the derivative of the something, the derivative of what was inside, the derivative of the u, or let's go back to the very beginning, the derivative of the y with respect to x. I strongly advocate that we as students use the dy over dx notation for our implicit differentiation instead of the y prime. I think it's very easy later on to confuse a y prime with a y to the first. So let's go ahead and stick with the dy over dx notation. And that would actually complete our example B. Now before I go on to example 1c, if we return to example A for just a moment, and if you think about, well, wait a minute, could I have done example A in a very similar fashion that I did example B? Would I have the ability to tack on the derivative of the something? Well, you certainly could, but since that something was an x, the derivative of x with respect to x would be a 1 anyway. So I say sometimes to my students that if you get confused about, hey, when do I use the chain rule and when do I not use the chain rule? And I sometimes will say, well, you use the chain rule all the time. It's just that it doesn't really have any significance when your variable is an x to begin with. All right, we'll take a look at C now. We're going to take the derivative of both the x and the y. The derivative of x with respect to x is, of course, 1. Not too bad. And we will add to that, and I always get a little chuckle when I ask students this, what is now the derivative of y with respect to x? Kids will think about that for a little bit, and they many times will spit right back the question that I asked. They'll say dy over dx, and I say that's exactly right. That is the derivative of y with respect to x. Of course, you could think of that as having a 1 in front, something like that, but that's pretty silly to write because the 1's not going to have any meaning, so it's not necessary. So this would be our derivative of x plus y with respect to x. Now, our first big challenge here, I think, comes in the form of example D. We're taking the derivative of x times y squared. And if you were listening carefully, you may have heard me say the word times, which I'm hoping that brings about the whole idea of the product rule. So in order to take the derivative here, we would use the product rule. I will start it up with the derivative of the first piece, which is 1, multiplied by the second piece, y squared. Add to that the first piece, x, multiplied by, now here we go, the derivative of the second piece. This is where this implicit differentiation idea really gets utilized. The derivative of y squared with respect to x would be 2y to the first, and then we tack on the derivative of y with respect to x. And there's really nothing that can be done to truly simplify this outside of rewriting it perhaps without the extraneous 1's. You could remove some dots here and maybe place the 2 in front of the xy, and you could follow up with the dy dx at the very end. And that's about as good as it's going to get. Implicit differentiation is a little different, but it takes just a little bit of practice with some of the basic kinds of expressions like this to become very good at it. Next, in another video, we're actually going to tackle a little bit more of a complex equation, a complete implicitly written relation. Notice I will not say the word function all the time because a lot of these implicitly written equations are not functions. They will not pass the vertical line test. But some of these equations that we encounter are going to be a little bit more challenging to take a derivative, but they're also going to have some very interesting graphs. Hope this helps. We'll see you next time.